Okay. Sorry for the inconvenience. There was like a tiny technical problem with the Zoom meeting, but we are here now. So today I'm going to talk about this interesting paper about learning end-to-end goal-oriented dialogues. It's a paper from the Facebook. So here's the outro, and then I will the objective of what the approach to send. So most of the dialogue you, for instance, like talking to a chatbot for a bank from a bank. So you go, you want to check your account, you just have like some simple query, and then you just interact with the chatbot, and the chatbot is able to provide some results for you. So these are mainly goal-oriented or slut feeling. So by slut feeling, it means that it asks for some specific questions, and then it extracts or figures out the goal or the objective of the conversation. So the problem with slot filling dialogue systems are that they are hard to scale to a new domain. If you train a chatbot for instance, for like a restaurant reservation, then it will only work for restaurant reservation. If you want to apply it to another domain or for another application, you need to start from scratch and train it again. So on the other hand, we have end-to-end dialogue systems. So what are end-to-end dialogue systems? So these are chit chat, or we can call them chit chat chatbots. So they are trained on the past dialogues. Mainly, for instance, you can train them using the movie conversations. You can train them from, for instance, I worked on like a tiny chatbot. I trained it on the Reddit threads. For instance, people start commenting, people ask a question, and people start commenting. So these are like the normal sort of conversations, and then you can train them using like a sequence to sequence model. They perform well in non-goal oriented setting, but they're not good at goal oriented setting or like achieving an objective through conversation. So the main question that paper asks is, can end-to-end dialogue models be competitive with traditional methods or goal-oriented and transactional dialogue systems, even in the well-defined narrow domain task where they excel? If not, where do they fall short? So this is the question that we will be answering by the end of this presentation. So this image from the paper explains a lot of useful information. So this is like the main idea behind a goal-oriented chatbot. So for instance, the user wants to reserve reserve some seats in a restaurant. So as you can see, user starts like with a simple conversation, and then the conversation is divided into different tasks, mainly four category of the task, and then task 5, we can call it the whole dialogue, how to carry out the whole dialogue. We can say it's task number 5. We will talk more details about tasks in the next slide. So so this image explains how a goal-oriented dialogue system works. User starts with like asking some questions, and then the system or the goal-oriented dialogue is responsible to provide meaningful answers and ultimately achieve the goal, which is reserving some seats in a desired restaurant for the user. And I think we will come back to this when I'm talking in more details about the tasks. So the goal here is explicitly not to improve the state of the art in the narrow domain of restaurant booking. So this paper mainly focuses on a specific domain, which is booking a restaurant, but the main goal is not to just improve or like build the best sort of a state-of-the-art dialogue system for reserving restaurants. It's mainly to take a narrow domain where traditional handcrafted dialogue systems are working well, and then use that to gauge the strengths and weaknesses of the current end-to-end systems with no domain knowledge. So yeah, the end-to-end systems, they do not have the domain knowledge in booking a restaurant or making transactions, or in other domains that chatbots or goal-oriented chatbots are mainly used. So here we are trying to use or sort of gauge the strengths and weaknesses of the end-to-end systems. Okay, so the main objective of the paper. So here, in the restaurant reservation domain. So first thing that we should know, the data that they used for this paper, it's a simulated data. It's not like a real world data. So they simulated so they simulated the data, and it's all synthetic data. All the conversations, the goal-oriented conversations are simulated. So it's a simulation based on an underlying knowledge base that facts contain the restaurants that can be booked and their properties. So the knowledge base here is like a sort of like a big database of restaurants. And then you know all the attributes for this restaurant, the type of cuisine that they serve, their location, their rating, and also, for instance, for how many people do you want to reserve a table. The knowledge base also can be queried using API calls. So the goal-oriented dialogue system here, or I would like to call it like generally the chatbot, it's going to take the queries from the users, fill out all those slots. The slots, I mean, yeah, type of cuisine, how many people, what is the rating, where is the location. So those are the slots that the chatbot is required to fill. And then based on that, it can call an API. And then the API will return the list of facts related to the corresponding restaurant. So as I explained, yeah, each query must contain at least 4 fields: location, type of cuisine, the price range, and also the party size, how many people are going to be served. So talking about the tasks, how they have divided these tasks. Task 1 is issuing API calls. So by issuing API calls, so the chatbot needs to make sure to grab enough data to fill out those 4 slots. If the user starts a conversation, and for instance, the user, let's say, talks about the cuisine and price, but the user doesn't provide information about the party size or the location, so the chatbot needs to be able to ask questions so it can receive the location and also the party size, right? Task 2, updating API calls. So by updating API calls, it means that if the user changes their mind, for instance, at the beginning they talk about, I don't know, maybe Italian cuisine, and then after a while they say no, they want to change their taste and they want to like go for Mexican grill. So the chatbot should be able to update the API calls and change the query for calling a new for making a new API call. Task 3 is displaying options. So after calling the knowledge base and then getting the results, the chatbot should be able to provide detailed information about the options that it's going to provide to the user. Task 4, providing extra information. For instance, if the user wants to know, for instance, the phone number or what are, I don't know, some extra useful information. For instance, if there's any parking spot. So this kind of information, the chatbot still should be able to provide that kind of information. And then combining all the first 4 tasks together, the chatbot must be able to carry out the whole dialogue, the full dialogue. And then if the chatbot is not able to, for instance, carry out one of these tasks, then task 5 is failed. So if we quickly go back to the image, so as you can see, task 1, user starts, I'd like to book a table for 6 people in an expensive price range with British food. So yeah, it's the chatbot receives all those information to fill out those 4 slots, and then it starts calling an API, and then the user changes its mind and says, no, actually I prefer for 4. So the task 2 should update the API call, and then instead of six people, it should call for 4. And then task 3, out of those options, the chatbot is showing one of the options or recommending an option. And then in task 4, let's see. So task 4 is asking for the address, and then chatbot is able to provide the exact location. And then task 5 is showing that, okay, yeah, the dialogue system was able to provide or carry out the whole dialogue. Okay, so talking about the data set quickly. So the simulated data that they had, so they split types of cuisine and locations in half, and then created 2 knowledge bases or 2 databases. One with all facts about restaurants within the first halves, and one with the rest. So this yields 2 knowledge bases of 4,200 facts and 600 restaurants each. It means 5 types of cuisine, 5 locations, 3 price range, and 8 ratings that only share price ranges, ratings, and party size, but have disjoint set of restaurants, location types of cuisine, phones, and addresses. So why they did this? So they wanted to create 2 knowledge bases, first of all, and then train and validate on one data set or one knowledge base, and then test on another knowledge base or data set here. So, and the reason that they did that, they wanted to make sure that the vocabulary between these 2 knowledge bases are different, right? Because when they say they split the cuisine and locations in half, so one of these KBs is going to have totally different cuisine and locations from the other one. So that creates a sort of like a totally different vocabularies in conversations from like one KB to another KB. So it makes testing more fair. So in addition to those 5 tasks using all simulated data, synthetic data, so they wanted to also test it on 2 other type of data. One is Dialog State Tracking Challenge. So this is a challenge to test how chatbots are able to carry out the dialogue and achieve the ultimate goal. So they call it task number 6. So this is real world data, interaction between chatbots and human beings, and then see how they are able to test their model on this data. And also another thing that they wanted to test is online concierge service. So this is completely human with human interaction. There is no chatbot involved. So the conversations are very natural, And so this is like human talking to humans in sort of reserving in the reserving restaurant domain. So they also wanted to check how their model would perform in compare to a human versus human and human interaction. So the approaches, there are like 5 different approaches that they wanted to test. So rule-based system, so they built a completely rule-based based on the simulated data. So they came up with like different rules. If this word was in the user's query, then do this. And if, for instance, so they came up with a lot of if conditions, that if this word, then do this, if that word, then do this. So that's completely rule-based, based on the simulated data, only for restaurant reservation domain. And then the other approach, classical information retrieval models. So it's just figuring out the similarity of user queries to candidate responses, right? For the dialog system. So they have converted all the words into a bag of words using TF-IDF transformation, and then using the cosine similarity score to figure out how they are similar or different. And then based on the similarity score, they would provide a response. So they use TF-IDF with cosine similarity, and also nearest neighbor, which is another method in classical information retrieval. They have used, for nearest neighbor, they have used word overlap. So they are just checking for like a specific words, and then based on that, they would provide like a candidate response. The third approach is supervised embedding models. So this is like a classification problem mainly. So the main idea is to predict the next response given the previous conversation. So this is like word embedding. In like a word embedding, for instance, word to egg or glove. So you have the context, and then you want to predict one word, or you have a word, you want to predict the context. So this works in the same way. Here, you only the goal is to predict the next response given the previous conversation. So the previous conversation could be a few questions and few answers by the dialog system, and then you can predict what's going to be the next response. And also, the fourth approach is memory networks. This is like a class of new models which is mainly targeting the question answering downstream task in NLP. If you guys are interested, I strongly recommend go read the paper. The memory networks paper is also from the Facebook AI research group. So that's why they built or they did this research on top of that. So, and then at the fifth one is match type features to deal with entities. So this is very important, this one. When you're working with named entities in this domain, for instance, name of the restaurants, phone numbers, name of locations. So these are named entities. And then when you're building, for instance, word embeddings or supervised embedding models, these unique words, because they don't get repeated that many times during the conversations, so these named entities, they do not have very good word embeddings when you're training your model. So this creates like a huge problem later on. So when the chatbot wants to provide information, because the word embeddings of the name of the restaurants are gonna be close together. If you imagine it in a word embedding 2D sort of space, words that are similar together, they tend to stick in the same area in the 2D space. The same idea happens here, because the name of the restaurants tend to be kind of similar together when you're training for like a supervised embedding model. So making mistakes with the name of the restaurants or addresses or phone number can occur frequently. So what they came up with is that, okay, when we are mentioning the name of the restaurants or cuisine type or location or phone number, so we should augment a keyword that represents, for instance, for phone number, when you're giving the phone number, just augment the word actually phone number and then the phone number, the digits after that. And when you're mentioning the cuisine, when you're saying, I don't know, Italian, Mexican, or anything, just augment the word cuisine at the beginning of the word. So it's going to be like a match types on top of these named entities. So this is going to help the whole training, and then for the named entities, it's gonna sort of increase the meaningfulness of these word embeddings. So experiments, I'm gonna quickly only show this table. So this table has a lot of information, a lot of very good information. So starting from the left, when it says tasks, so you can see T1, T2, T3, T4, and all the way to T5. And then you have the same thing for out of vocabulary. So this is the second testing set or the second database that we talked about. So the vocabulary on the OOV or out of vocabulary. So the vocabulary is completely new. It's completely different from what was the model trained in the first database or in the first KV. So starting from the rule-based, you can see there's two columns. The first column is the accuracy score without brackets. So this is so let me read it for you. The first column is per response accuracy metric, and then the second column with brackets is per dialogue accuracy. What is the difference? Per response accuracy is how many responses the model was able to get correct. And then per dialogue accuracy is how many dialogues the model was able to get correct. When we say dialogue, we're talking about the whole dialogue, task 1 to task 5, all of it. If any of the tasks failed, then it was not counted as accurate per dialogue accurate. So as you can see, the rule base that they have built, it's perfect, right? It's almost perfect, except for the task 6, the dialogue state tracking, which is real world data, which is completely different from this simulated data. As you can see, the accuracy went down pretty bad. So the rule base that they have built for this simulated data, because they knew everything about the simulated data, that's why it's doing perfect. So moving on to the information retrieval, TF-IDF, you can see it's not doing well at all. For the per dialogue accuracy, you can see it's all zeros, and then even per response accuracy is not that good, even though they have added the match types. Nearest neighbor, the same, almost the same, a little bit better in per response accuracy, and still per dialogue accuracy, you can see it's not doing well. So moving on to supervised embeddings. So you can see for the task 1, which is issuing API calls, for the training set, the accuracy is pretty good, but the other tasks, it's not that good. And then per dialogue, you can see it's all zeros. But for the out of vocabulary, it's still able to keep up for the task 2 all the way to the task 5. So it means that, yeah, machine learning is doing its job here. When you train based on supervised embedding or like in a classification environment, so it can perform well, but not that well. You can see the highest accuracy for task 2 in out of vocabulary is 68%. So this is the highest accuracy they were able to achieve, which is not that good, I think. And then moving on to memory networks, which is like the main focus of this paper that they're talking about, that memory networks can improve the accuracy of end-to-end end-to-end dialogue systems by gauging the goal-oriented dialogue systems. So for memory networks, you can see for the training set, the accuracy is not that bad, 99.9%. And then also for the per dialogue accuracy, for instance, for task 1, 2, it's pretty good. But for the rest of the tasks, you can see that, yeah, the whole dialogue accuracy is not that good. And then for the out of vocabulary, you can see that the accuracy for per response accuracy is pretty good. But for dialogue, for the whole dialogue, it's not good, because the vocabulary completely changes, and then the memory networks are not able to catch up. But when you add the match types, or those important words to the named entities, right, you can see that, yeah, the accuracy is improving much better. Task 3, you can see, is quite challenging for per dialogue accuracy, and then the rest of them is kind of good. So, and also for the out of vocabulary, you can see that the accuracy is kind of similar to the training set. And then for task 6, you can also see that, yeah, the accuracy is not improving that much, but still memory networks are able to achieve the highest accuracy for per response for task number 6, which is the real world data. Real world data between the conversation of a chatbot and a human being. And for the concierge, you can see that rule-based doesn't apply to a concierge because the data is completely different. It's completely natural. And then if you want to compare something which is 100% natural with 100% simulated, that's not a good comparison. That's why they didn't do it. But overall, memory networks, you can see that are able to achieve the highest accuracy, which is 16.7, which is not a good accuracy. But here you can see that the memory networks were able to achieve the highest one. So overall, so the paper's objective is that this is going to be a promising area of work if you want to extend this research and then improve sort of the goal-oriented, to gauge the goal-oriented into an end-to-end dialogue system. Memory networks are strongly recommended to be sort of focused on. So that was the experiment results. And moving on to conclusion, I would like to read it from the paper, which is explaining it in like a very informative way. So they mentioned that we hope this will help foster progress of end-to-end conversational agents, because existing measures of performance either prevent reproducibility, different mechanical torque jobs, or do not correlate well with human judgment. The breakdown in tasks will help focus research and development to improve the learning methods. And finally, goal-oriented dialogue has clear utility in real applications. We illustrated how to use the test bed using a variant of end-to-end memory networks, which prove an effective model on these tasks relative to other baselines, but are still lacking in some key areas, as we saw in the results of the experiments. So yeah, this was the paper that I found quite interesting, and I hope my talk was good enough and I was able to transfer the idea. So let me know if you guys have any question. So simulated data is the data that you create based on a rule-based set of conditions. So in talking specific about like restaurant reservation domain, so I would say that you just go and, for instance, from like the concierge that data set that they use, you can go look over that data and then make some rule-based script, and then you can just create conversations.